So again, welcome to what I consider the last day of the entire year of mathematics that is new to show you guys. So it's a kind of a big day. For some of you, it's a monumental day of your life because it's your last day of math. For others, you may have a year or more years. Let me ask you, are there any questions at all about anything before I start talking about the quiz? Any questions? Okay, if there's no questions, let's take a look at that quiz. Okay, so we have the quiz. And consider the function f of x equals the square root of x. Find the Taylor series for this function centered at x equals 4. Okay. So to find a Taylor series of a function, if you remember, I drew a table, and I recommend doing that. So I have a table. So we can get a pattern out of it. So we have f. Then we're going to have, we're going to have n. And then fn of x. And then we'll have fn of 0. Fn of 4. Any questions on the table? Okay, if n equals 0, I'm hoping this is easy for everyone. What happens when you plug in 0? Actually, sorry, before 0, that's going to be root x. And I'm just going to go rx, call it. That way I don't have to go into the whole equation editor. Hopefully that will be okay with you guys. That means root x. And then if you plug in 0, what do you get? Plug in 4, what do you get? Supposed to be easy? Yeah, 2. Okay, if n equals 1. Well, now we want to think about root x as x to the 1/2. You get 1 over 2 times x to the negative 1/2. And now if I plug in 4, what do I get? Okay, so I get 1 over 4, but I'm going to write it as 1 over 2 times 1 over 2. Remember, if you do the arithmetic, it might be a little harder to see the pattern. Whereas if you leave the arithmetic alone, then patterns will show a little better. If n equals 2, okay, then we have 1 over 2 times, and actually negative 1 over 2 times 1 over 2 times x to the negative 3/2. Any questions on that? Okay, and now what we're going to do is we're going to plug in. So we get negative 1 over 2 times 1 over 2, and then times, and then 4 to the negative 3/2 is the same as 1 over 4 cubed. If n equals 3, so we get negative 1 over 2 times 1 over 2 times negative, so the negative goes away, 1 over 3, and then times x to the negative 5/2. And then what we get is negative 1/2 times 1/2 times a fourth, times a third. Wait, just a minute.
Larry,
that's not 1/3. That's 2/3. I knew
Larry,
something wrong. Yeah.
can you scroll down a little bit?
Oh, sure.
Thank you.
As I forget that you can't see the bottom of my screen. Sorry about that. That's a Zoom thing. Okay.
Yeah.
Times 1/2 times 2/3, and then times And again, and let's see, that was 1/2 to the third actually. And then times 1/2 to the fifth. Okay, let's go to 4. So we get 1/2. I know it's getting long, but you'll see at this point, hopefully we'll see it. Times 1/2 times 2/3. And then times 5/2. And it's a negative in the front. X to the -7/2. And then I'm going to copy and paste all these numbers here. Can copy and paste that part. And then times 1/2 to the 7th. Okay, we're getting there. Sorry, this is not 5/2, but 2/5. Okay, let's do one more, and then one more we're going to do is the pattern. So now let's do n. So let's look at this and see what we have as a pattern. So first thing, I think I made a mistake here. 3/2, yeah, this should be 5/2. That was right. 3/2, sorry about that, I made a little mistake. Actually, 3/2, 3/2. And 3/2, 5/2. Okay, so now let's look at the numerator and let's look at the denominator. The numerator, we have, notice that it's positive. So it's going to be positive, negative, positive, negative, positive, negative. So we have an alternating series. Okay. Or here, we have an alternating series. The first term is a little off. So I'm going to ignore the first term and we'll put that in later. We're going to start at 1 and we'll just go 2 plus. But notice we have plus, minus, plus, minus, plus, minus. So we're going to have -1 to the n plus 1. Because notice for the odd ones, you get a negative, and for the even ones, you get a positive. Times. And now what we're going to have is, we're going to have 1, 1, 3, 5. Do you see that? And the next will be 7, then 9, then 11. So notice that it's the product of the odd numbers. So I'm going to write that as 3 is 1 times 3, actually just 3 times 5 times 7 times times 2n plus 1. Sorry, minus 1. Let me double check. 2n minus 3. Because notice 4 times 2 is 8. 8 minus 3 is 5. And then the denominator, well, we have a 2, a 2, a 2. Notice we have a 2, a 2, a 2, a 2. So that'll be a 2 to the n. And then times 1 over 2 to the, and here we have a 7. There's going to be a 2n minus 1. Any questions on the pattern? Okay, now what I'm going to do is I'm just going to put it together. So I'm going to copy what I've got from my n. Now I can say that the function f of x is equal to, you know what I need? To put it in equation mode, it's too messy this way. Won't let me. All right. Okay, so f of x equals, I'm going to redo this. -1, that's right, summation. And we had a 2 plus summation. Sub n equals 1. To infinity. And it doesn't like this, so I'm going to type it. -1 to the, nope, to the n plus 1. And then times the fraction. 3 times 5 times 7. Dot, 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 times 2n minus 3. Over 2 to the n. Times 2 to the 2n minus 1. So I can actually put that together. It's 2 to the n times 2n minus 1. No, n plus 2 minus 1. Because we're multiplying, that becomes addition of exponents. Or 3n minus 1. Now I get rid of all that stuff. And that's going to be times x minus 4 to the n. And let's save it. Whoa, it didn't like it. Okay, well, you saw it. There it is. Any questions on that? Kind of messy. The next one won't be as bad at all. Next one's quick. I notice the points are the most for the first one. Okay, for the Maclaurin series, e to the negative x, which is a summation of -1 to the n over n factorial x to the n. Find the maximum absolute error when using -1 to the n over n factorial, n equals 0 to 4 to approximate 1 over e. All right. So what do I do here? This is an easy one. That's a hint. What does the theorem tell me? So what's the theorem tell me about maximum absolute error? Guys, remember? I don't see you all jumping in. Yeah. So you look at the maximum of actually the next term. Okay, so we're going to look at the next term, and we can take an absolute value of that. So the -1 to the n goes away. And notice, by the way, you could take derivatives all you want of e to the negative x. And all you get is either plus or minus e to the negative x. Is that clear? So just note that between 0 and 1, because that's what we're doing, this is a Maclaurin series. It means that is at 0, and we're plugging in 1 for x to get this guy. That's why the x to the n goes away, because 1 to the n is just 1. So between 0 and 1, the maximum of e to the negative x is just going to be 1, because it's e to the negative, because it's e to the 0 is the maximum. So the maximum of the fifth derivative, or any derivative, because that's one of the nice things about e to the negative x, is 1. Therefore, the maximum error means we just plug in 1 into the fifth term, is 1 over 5 factorial. Which is 1 over 5 times 4 times 3 times 2. So that's 20, 60, 120. 1 over 120. Any questions at all on that? So that was supposed to be a much easier one, question 2, because you just plug in. And that's it. Any questions on the quiz? Any questions? Okay, any questions about anything else as I move over to new stuff? Okay, if there's no questions about anything else, I want to get into the last stuff. And what this section is, which is what I like for a last section actually, it's all of the nice, cool ways you can actually use, or it's a lot of the cool ways you can use Taylor series. And the first item is binomial series. So I want to just give you a little reminder, something that you should all be able to do long but easily. Let's do it. Let's do a basic example. What if we had 1 plus x cubed? How do you do that? If you want to multiply that out.
Couldn't you FOIL the first 2 terms and then distribute the third?
Yep. Yep. You could FOIL the first 2 and distribute the third. And I think I'm going to spare you of the pain and just do it and just tell you here it is because I have it memorized. 1 plus 3x plus 3x cubed plus 3x squared, sorry, plus 3 plus x cubed. You all believe that?
Yeah.
So whenever you have a 1 plus x to a power, you can just do that. Is that true?
I'm pretty sure.
All right. If you're sure, let's see if you can do this one. Notice I'm smiling. What if we had 1 plus x to the, how about 2/3? Could you just FOIL it out?
No,
What's the problem?
it's a fraction.
Yeah. But can it be done? The answer is yes.
Yeah.
Okay, so notice that when you had 1 plus x cubed, you ended up with a power series that just stopped on the x cubed term. Do you see that? Okay, because the other way, by the way, the other way of doing the 1 plus x cubed is say plug in 0. If you plug in 0, you get 1. Do you see that? Do you all agree? Take a derivative and you get 3 times 1 plus x squared. Then plug in 0 and you get 3. There's your 3. Take a second derivative and you get 6 times 1 plus x. And then remember, you're taking 6 divided by 2 factorial, and that's 3. And that's why the 3x squared. And then take a third derivative and you get 6 over 3 factorial times x cubed, which is the same as just x cubed. Take a fourth derivative and you get 0 for the fourth derivative. Do you agree? That's why there is no x to the 4 and the 5th derivative and the 6th derivative. So you could actually, and you don't actually have to FOIL this out. You could do this with power series. Do you all agree?
Yeah.
Okay. Well, guess what? That means we could do this one with power series also. Any questions on that? But instead of doing this example, this is one of the weird type things where doing every single possible case at once is easier than doing an example. Is that weird? So I'm going to do every possible case at once. And then we can go back and do the 2/3 very easily. So let's look at, so find the power series for, and what I'm going to do is make an equation out of it. 1 plus x to the r, where r is some power. And everyone tends to use r, I don't know why, but they all do. Any questions on the goal here? And in fact, let me write down for the binomial, 1 plus x to the r. They call this a binomial because binomial means there's 2 terms and we got 2 terms to a power. Any questions on this? Okay, well, let's go do it. And the way you do it, hopefully you remember, is you draw a table. And let's play around. So we're going to have n. We're going to have fn. Of x. And then we'll have fn of 0. And n will start at 0. Fn of x is just 1 plus x to the r. And this is easy. What happens if I plug in 0?
1.
Yeah, 1. So Victor's asking if this is called the binomial theorem, and the answer is yes, it is. And we're going to get there. But I haven't written the theorem down, right? Basically, I'm doing the proof before the theorem. I think it's a better way of thinking about it. But yeah, so we'll get there. So this is going to be the binomial. It's going to allow us to get any binomial as a power series. All right, and then n equals 1. What's the derivative of 1 plus x to the r?
R times 1 plus x times 1.
Close. It's r times 1 plus x. But the power now, remember when you take a derivative, you subtract 1.
Yep.
R minus 1. You can write times 1, but most people don't write times 1. If I plug in 1, what do I get? If I plug in 0, what do I get? It's easy.
R to the r minus 1.
No, just r. Because notice that we get r times 1 to the r minus 1. And 1 to the r minus 1 is just 1. So it's just r. Is that clear? So now let's plug in 2. Okay, let's let n be 2, I mean. So then let's go and look at this one. This is going to be r times r minus 1 times 1 plus x to the r minus 2. Okay, and if you plug in x equals 0, you get r times r minus 1. Let's go 3. So I think I'm going to do a copy and paste. I think it's easier. So it'll be r times r minus 1 times r minus 2 times 1 plus x to the r minus 3. And you get r times r minus 1 times r minus 2. Okay, at this point, you might see the pattern. So if I want the nth one, what is it?
R times R minus N.
It's more complicated than that. It's r times r minus 1 times r minus 2 times dot, 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 times r minus n minus 1. Okay, or if you want r minus n plus 1. Any questions on how that happened? Notice that if we're n equals 3, we stopped at 2. Any questions on that? So in particular, we're going to stop kind of 1, or we're going to go r minus 1 less than what our n is. Any questions on that? Okay, I guess I don't need this particular row. There we go. All right, now we're ready to put things together. Okay, and what we get, this is the theorem. And this is the binomial. And it says the following. Just a second. What it says is that the Taylor series expansion of 1 plus x to the r is, and what we're going to have is we're going to have a summation with one of these. There it is. It's going to be a summation, and as usual, we can go n equals 0, and we're going to go up to infinity, because that's how Taylor series works. And what we're going to have is we're going to have a fraction. And we're going to have r times r minus 1 times r minus 2 dot, 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 times r minus n plus 1 divided by n factorial, because that's all part of the Taylor series formula. Times x minus 1, sorry, not x minus 1, just times x to the n. Any questions at all on this big theorem? Any questions? All right, one of the interesting things is I used to really kind of skip this part because I thought it wasn't that important. And then 5 years ago, I did my sabbatical on where math was used. And I watched hundreds of lectures and cataloged where they use calculus. And this was number 1. And I'm like, I can't skip this. This is where it's used in physics and engineering and all kinds of places. So this is a biggie. Okay, it's not a very big one if you're a math major. It's a big one for engineering and it's a big one for physics. So just let you know, this comes up in all over the place in the real world, even though it looks just kind of weird, but it's actually a really important one. Any questions on this big theorem? So now that I have this, I can answer my question. How about 1 plus x to the 2/3? So what I can say is I can just copy I could say 1 plus x to the 2/3 is equal to, well, r is 2/3. So it's 2/3 times, what's 2/3 minus 1? Hope you can all tell me that. Yeah, negative 1/3. What's 2/3 minus 2?
Negative 2/3.
Negative
4/3.
4/3. Negative 4/3. And then I can just go 2/3 minus n plus 1 over n factorial x to the n. And there's my series expansion for 1 plus x to the 2/3. So it's very easy, if you have an example, to just plug in. Do you agree? You have to know how to subtract fractions. Some people have trouble with that. But that's it. Any questions at all on the binomial theorem? Okay, why would you care about this? How do you think this is used? Because it's used everywhere, I said. Any ideas? Okay, the idea is whenever you have a fractional exponent, whether it's a half or a 2/3, whatever power it might be, we can always write it as a power series. And remember, a power series, you can truncate into a polynomial. And polynomials are much easier to work with than fractional exponents. Whether you're using a computer or whether you're doing differential equations or integration, whatever you're doing, it's much easier. Okay, what if I told you, to do some integral where it had an 1 plus x to the 2/3 involved in it? Okay, especially if that was with, multiplied by, or multiplied by 1 plus x squared or something, you wouldn't be able to do it. But if you turn it into a power series, you can. And that's why it's used, is it takes these fractional exponent stuff and turns it into things that look like polynomials. Any questions on that? That's where I want the equals. Any questions? Okay, so that's the binomial series. And again, it's used a lot. So let me go and talk about what we're going to do. So now we want to find series using known series. Okay, very important is how do you if you have a series that you don't know and it looks a little like what you do know, you can get it. So let me give you an example. So find, I don't need it so big. Find the series for f of x equals the inverse tangent of x. Okay. Any questions on the question? Okay, and we can do it at x equals 0 because that's always easiest as long as it's a nice function, and it is. Tangent, inverse tangent has no troubles at x equals 0. And there are two ways of doing it. One way is draw your table and start taking derivatives until you can find a pattern. But here's something I'll tell you. You won't find a pattern, you'll just go crazy. Sound good? So we could try it, but the problem is the inverse tangent, you get 1 over 1 plus x squared, and you take a derivative of that, and then it starts getting messy. Okay, you're going to have to use chain and product and quotient rule, all kinds of stuff. So any other ideas on how you might do this? One idea is 1 over tangent, except inverse tangent is not 1 over tangent. There's the arctangent. The 1 over tangent is the cotangent. Do you remember that? The inverse tangent means that it's the inverse function of the tangent of x, not the reciprocal of the tangent of x. Do you remember that? So this is not 1 over tangent. So any other ideas on how you might come up with a power series for the inverse tangent of x? Okay, so let me remind you something from last quarter, okay, that we did a lot last quarter. And that is f prime of x is equal to, who remembers the derivative of the inverse tangent of x? That was an important one last quarter.
Isn't it 1 over 1 plus x squared?
Yeah, 1 over 1 plus x squared. You remember doing that? Okay, so that was really important, and we're going to use that. Let's make this a little bigger so you can see it better. There we go. Okay, now you look at that and say, does this have a power series that's friendly? The answer is yes, and tell me why. Without even, you don't have to make a table for this one.
Geometric.
This one is a variation of the geometric series. So what we can say is that this function, 1 over 1 plus x squared, is equal to the summation of, well, the r in this case is negative x squared. So I'll write that down, negative x squared to the n, which is equal to the summation of negative 1 to the n. It's always a good idea to pull the negative out, by the way, times x to the 2n. Any questions on that algebra there? Calculus and algebra. Okay, now that is not the power series for the arctangent of x. That's a power series for the derivative of the arctangent of x. Do y'all agree?
Yes.
So how do I find the power series for the arctangent of x? Yeah, we integrate. So then we can say that the arctangent of x is going to be equal to the integral of negative 1 of the summation of -1 to the n power times x to the 2n dx. And the great thing about power series is that integrals are always easy. So if you ever think you have to do some kind of evil rule, you're wrong. Okay, it's always easy. So the idea is the -1 to the n, that's a constant. There's no x in it. So we're just integrating x to the 2n, x to a power. And that is equal to the integral. That is equal to the summation of -1, and let me make it as a fact. Let me make it as a fraction. So -1 to the n divided by 2n plus 1 x to the 2n plus 1 plus c. Don't forget we integrated, so we got a plus c. Let's make that a little bigger so you can see it. Any questions on that? How do I find c?
I would assume we'd have a little bit more information.
No, that's all we need. You have to know about the arctangent. The hint is it's really easy. Even though it looks horrible, it's actually easy. Okay, all you do is plug in 0 for x. Remember, this plus c means it works for all x. So choose the easiest x in the universe, and that's 0 in this case. What's the arctangent of 0?
0.
So we know that 0 is equal to, and now let's look at the summation. Notice that we have an x to the 2n plus 1. This starts at n equals 0. Remember, if I don't write it, it means it starts at n equals 0. If n equals 0, we have an x to the 1. If I plug in 0, I get 0. Everything else is x to even higher powers, and I always get 0. So 0 is 0 plus c. And if you don't know how to find c at this point, then you don't belong in my class. If 0 is 0 plus c, what's c?
0.
C is 0. So c equals 0. Okay, so in particular, we can say that the inverse tangent of x is equal to, I better just pop that guy in. I don't want to type it again. The summation -1 to the n over 2n plus 1, x to the 2n plus 1. Notice that the inverse tangent of x is an odd function, because we only have odd powers of x. Okay, and that you might have learned from trig also, I don't know. But it's really easy in power series to know that it's an odd function, because 2n plus 1 is odd. Any questions on this example? Okay.
Pretty interesting how you can rewrite a function as a series.
Right, and not just a function,
Any
function
function.
that has an infinite number of derivatives. And remember, even like the square root of x, which doesn't have a derivative at 0, well, you can write that as a power series, just center it at 1 instead, and that's binomial. So pretty much every function that you've ever learned in your life can be written as a series. Isn't that nice? Isn't that beautiful? And the great thing about series is two great things. One is that they're just long polynomials, and long polynomials are much faster for computers to handle. Okay, and in fact, and this, you're gonna have to trust me on this, if you go into the libraries in any computer language, whether it is, Java or JavaScript or Python or whatever, the way the detailed code for the library for sine of x is it does a power series. That's how they work. So whenever a computer calculates a function, like, just your basic calculator, that's what it's doing. It turns into a power series. And there's, by the way, it doesn't do it. What happens is that somebody programs that if they see SIN, then that makes it, a power series, and that works. Let me give you another example. Take an integral of, and you could take an integral of anything. This is a big one that comes up in applications, and that's the sine of x. Let's do it as a, and I did this last time, but I didn't talk about it. Today's the application day. It's like, how do you use this stuff? Sine of x. So last time, you may or may not remember, but we calculated, and remember the sine of x? Remember that? That was -1 to the n over 2n . And remember, the sine of x is an odd function, so that's how I always remember it. 2n plus 1 to make it odd, factorial, x to the 2n plus 1. That's messy, isn't it? But now let's expand it out. Not all of it, just a little of it. Equals. Well, if you look at the n equals 0 term, that's easy. -1 of the 0 is 1. 2 times 0 plus 1 factorial is 1. And you just get x. Plus. Then you let n equals 1. And if n is 1, you just get -1 over, let's make that fraction. So -1 over, and again, if n is 1, 2 times 1 plus 1 is 3, 3 factorial, 6, x cubed. Plus, dot, dot, dot. So one of the great things about sine of x is if you're okay with a quadratic approximation, what is the sine of x? What's the sine of x? Sine of x is about x. And that's good to quadratic because remember the quadratic term is just 0. So that is good up to quadratic. So x is very close to the sine of x as long as you don't get too big. Okay, as long as you stay under 1, then x is close to the sine of x. And there's 1 radian, by the way. And 1 radian is pretty big. So this is a very nice approximation of the sine of x. And we can see that it's actually good up to quadratic, not just linear, even though it looks linear. Any questions on the sine of x? Any questions at all? Okay. And similar, you could do all kinds of different things. So for example, what if we wanted x squared times cosine of 3x? And we want a power series for that. What could we do?
You could take derivatives until you got 0.
You could do that, but that's no fun. So instead, if you remembered from 2 days ago, I did the cosine of x. Yeah, we know the power series for the cosine of x. And you just stick stuff in. So you have an x squared. I'll just leave that as x squared times the summation. I'm always having trouble with summation. Summation of, and remember cosine was the even one, so that's got the 2n instead of the n. That's how I remember sine and cosine. And we can say that is equal to -1. Whoops, what just happened? Somehow it erased everything. There we go. So that's -1 to the 2n over 2n factorial. And normally be x to the n, but it's not x to the n. What is it? Three x to the n. Any questions on that? Now I can simplify that, and I am going to copy and paste and then adjust, which is a typical math thing. So the -1 to the n to -1 to the 2n over 2n factorial, that stays. I could take that 3 and pull that out. And put that as the 3 to the n up on there. We want to get it away from the n. And then we have an x to the n. Actually, that x to the n, that should be x to 2n. We have an x to the 2n. But we also have an x squared. So I can rewrite that as x to the 2n plus 2. And there's my power series for x squared cosine 3x. So once you know your basic power series, there's all kinds of other power series you can do. Any questions on that? Okay, so that's an example. Again, we can make lots of power series once you know a few. So the next is, how do you solve a differential equation? And I'm just going to do a little of this, not a lot. So solving differential equations. And I can do it by example. I'm not going to do the whole thing. I'm just going to do a bit. If you want to see the whole thing in detail and really get good at it, what do you have to do?
Wait till next spring.
Yep, exactly. Wait till next spring. Not quite 12 months from now, more like 11 and a half months from now. It is towards the end of the differential equations class. And then you'll be doing lots of these. But for now, I'm just going to kind of give you an example and kind of show you the idea. So the first thing is, let's suppose we have a differential equation. Let's suppose we have y double prime how about plus x y prime equals, how about x plus 1? Okay, and you might even have an initial value. Let's suppose that y of 0 equals 1 and y prime of 0 equals 2. Just an example, just making one up. I want to solve this differential equation. All right, well, you look at this, and if I told you I'm thinking of a function, and if I take the second derivative of the function, I add it to x times the first derivative, then I end up with x plus 1. Do you have any idea what that function is?
Not at all.
No chance. But you do. Here's what the function is. As soon as I say it, you'll say, of course. But it's kind of cheating. So here's the solution. Y is equal to, this time I need the numbers for a reason I'll talk about in a bit. N equals 0 to infinity. Of a sub n x to the n. There we go, I'm done. There's my solution. Do you believe me?
Yeah, why not?
Sounds good, right?
Mhm.
But here's the problem. Do we know the ANs?
No.
We don't. So guess what? Now we find them. Okay, so you start out saying, well, the solution is that. I don't know the ANs yet, but I have a way of finding them. And what I do is I say, well, what is y prime? What is y double prime? Y prime is equal to, and I'm going to copy and paste what y was. Except now it's going to be an times n, x to the n minus 1. And this is why I put the numbers in, because it's now n equals 1 when you take a derivative to infinity. And then y double prime is equal to, I'm going to get rid of the word solution now. An times n minus 1 times x to the n minus 2. It's a bit too big. Doesn't work. I hate that. We'll get there. Okay, so there's our list. And what do we do now?
I mean, we are given initial values for y.
We're given that, but that we're going to use last, actually.
Okay.
We're given the difference equation, we just plug in. So what we can do is we can plug in the y double prime. And then we can go plus. And then we can plug in the y prime and multiply by x. And when you multiply by x, the n minus 1 becomes an n. And that is equal to x plus 1. Any questions on that? Okay, the next thing we can do is say, well, if y of 0 is 1, that means a0 is 1. Because remember, a0 is y of 0. So let's just write that down. A sub 0 equals 1. And similarly, if y prime of 0 is, that should be equal to negative, equals to 2. If y prime of 0 equals 2, then a1 equals 2. Any questions on that? Okay, but now we could look at these guys and we can say, well, we have these two sums equals this. I can take that and I can expand it a bit. So now let's expand it. And again, we know A naught, we know A1, okay? And that's important. So we can expand it and if n equals 0 here, you just get 0 on the first one. If n equals 1, what do we get? We get 0 again. Do you see that? If n equals, and in fact, usually you don't start at 0. That was my mistake. You should start at 2. If n equals 2, you get 2 an period. 2a2, a sub 2. Plus, if n equals 3, we get 3 times 2, which is 6, a sub 3 times x to the 1. If n equals 4, you get 4 times 3 is 12, a sub 4 x squared. And go plus dot dot, oops, plus dot dot dot. You could do more, but I don't want to waste your time. And then I could do plus, and I could do this sum, the second sum. If n equals 1, I get a1x. Okay, and in particular, actually, if n equals 1, a1 is 2, so you just get 2x. Plus, if n equals 2, I get 2a2 x squared. Plus, if n equals 3, I get 3a3 x cubed. If n equals 4, I get 4a4 x to the 4th. Plus dot dot dot. I think I'll stop there. Equals x plus 1. Any questions on that? Okay, so now I look at that equation. I can get rid of this a naught equals 1. I already used that. I can look at this equation and say the constant term, the only constant term is 2a2. You see that? All the rest of them have x's. The only constant term on the right-hand side is just 1. So what do I know about a sub 2? So what's a sub 2? Yeah, 1/2. Okay, then I go for a sub 3. Well, I can look at the x term. I have a 6a sub 3 plus 2 equals 1. So 6a sub 3 is negative 1. So a sub 3 is negative 6. Okay, and I could keep going. I could do the same with a sub 4. And if you do a sub 4, you'll notice there's an x squared term, and we have 12a sub 4 plus 2 times 1/2 plus 1. So plus 1 equals 0. So a sub 4 equals negative 12. And I can keep going as long as I want. And I can solve this differential equation to as many terms as I need. So I could do 100th order solution, and that's probably good enough for anything. So this is like a sledgehammer for solving differential equations. Any questions on this idea? Okay, and it turns out with this one, you can actually see a pattern eventually, and you'll be able to come up with a solution using pattern recognition. Sometimes you can't even see a pattern. But trust me, if I kept going, I'd eventually see a pattern. But only because I know differential equations well enough. Any questions on solving differential equations? Okay, so now I want to get into something really important. And I'm just looking at the list. I know Kristen is here, so she knows it. And that is the normal distribution. Kristen, do you agree the normal distribution is important? And I'll do the standard normal distribution. So I don't know if you're paying attention or not. I don't see anything in the chat box, but hopefully you agree the standard normal distribution is like essential in everything. Okay, it is the statistics tool. Also, if you're dealing with chemistry and you're dealing with orbitals, normal distribution is everything there. Same thing if you're dealing with anything in quantum physics. It comes up in economics. It comes up everywhere. And we don't have any, even a blink of time to talk about all the applications. But you can trust me that this is one of the most important things in all of mathematics. And here's the problem. If you want to find a probability, then it is, so the probability of X being between A and B is defined by the following. P, A less than X less than B is equal to the integral from A to B of P of X dx. Let me go F of X, where F is what's called the probability density function, dx. Doesn't sound too bad, does it? Any guess on what the problem is? Yeah, the problem is going to be F of X. So for the standard normal distribution, there's an issue. And the issue is, you won't see it until you think about it for a moment. F of X is equal to 1 over the square root of 2 pi, I believe. E to the negative x squared over 2. So what's the problem? If we want to find a probability for a normal distribution, what's the big problem? And it's a big problem. Yeah, if you remember from last quarter, this was the one I hammered it over and over again last quarter. This was the one you can't do. Okay, or at least you couldn't do last quarter. Why can we do it now? Why can we integrate it now? Yeah, now we can turn it into a power series, and power series are easy to integrate. But that's like a main reason why we care about power series. is so we can integrate things that you couldn't otherwise integrate. So in particular, the probability A is less than X is less than B is equal to, I can take the 1/√2 pi outside. That's not a problem. You can always do that with integrals. And then I can integrate from A to B. And I can also take the sum outside, and that's a big deal, actually. You're allowed to do that because it converges, absolutely. I'm just going to do sum. And what you get is we have an e to the negative x squared over 2. But remember, e to the x is x to the n over n factorial. So what we can do is we can put that together, and we can say, well, that's going to be a -1 to the n, x to the 2n. And then we have an over 2, so that becomes an over 2 to the n times n factorial dx. That looks horrible, but it's not. You all agree this is an easy integral? No matter how ugly and messy it is. You don't need any kind of, trig substitution or even U substitution. I mean, you don't need anything really. So hopefully you know how to integrate this. And let's do it. So what you do, and I just redid this, I'm going to get rid of the integral. If it lets me, I don't know if it'll let me. There we go, I'll go x, and then I can get rid of it. So we still have a -1 to the n over 2 to the n n factorial. But now when you integrate x to the 2n, you're going to have a 2n plus 1 in the denominator. And you're going to have an x to the 2n plus 1. Any questions on this? I want to mention something, right? We just did a whole lot of fancy stuff to write an integral as a summation. Why is this better than what we did in the first week of class last quarter when we just turned an integral into a summation? Anyone, any guess? This is something you might just guess, and then I'll explain in a little bit. Right? You could just do, left rectangles or right rectangles. But why is this one better? I don't see y'all jumping in. It's better because of this n factorial in the denominator. N factorial is gigantic for big N. As soon as n is, say, 20, n factorial is gigantic, gigantic. So this series, you don't need a lot of terms to have a really good answer to, say, 10 decimal places. Probably 6, 7 terms is all you need and you're done. And you get as many decimal places as you could ever imagine. Whereas if you do left rectangles, you might need 1 million terms to do, a whole lot of decimal places. Does that make sense? So this is a lot more accurate than left or right rectangles. Any questions on this? Okay, if not, let me give you the last application of the whole quarter. And that is looking at, and this is going to look a little weird, we're going to look at e to the ix. Doesn't sound important. You think it's important? What do you think? Yeah, this is really important for advanced physics. So when you get into upper division physics, you're going to see this every day, just pretty much every day. you're going to have an e to the ix. So at this point, trust me, but it is. So e to the ix, well, the nice thing about it is I can write this as a power series quite easily. So let's take a look. So hopefully you've gotten used to the power series for e to the x because that's the biggie. So e to the ix is the summation of ix to the n over n factorial. Any questions on that so far? And by the way, I is not a variable. What is I? And it doesn't mean me. What's I?
Square root of -1.
Yeah, square root of -1, which seems like ridiculously stupid because there isn't one. But for some reason, and this is like one of the mysteries of physics, is that it's everywhere in physics. And don't ask me why, that Mother Nature, religion, or whatever has decided that that's everywhere, but it's everywhere, and it has to be. So it's just weird. So we can rewrite this, and we can think about this interestingly as a summation of I to the n, x to the n, over n factorial. Any questions on that? Okay, now let's think about I to the n. Well, I to the n is interesting. What happens if n is even? What happens if n is even? What is I to the n? What's nice about I to the n if n is even?
It's actually a real value. It's
a real value. And if I is odd, it's always imaginary, right? So I could rewrite this and split it up into the even terms and the odd terms. So this is equal to, and now let's think about it. I'm going to do the even ones first. So if it's even, then we have I to the 0, that's 1. I squared is -1. I to the 4th is 1. I to the 6th is -1. It's an alternating series, right? So this is equal to the summation of -1 to the n still have over n factorial. Sorry, not n factorial anymore. Now we're going to have 2n factorial because we're only going to do the even ones. X to the 2n. Plus, now let's do the odd ones. Well, if you do the odd ones, you're always going to have an I. And I'm going to pull that I out. And then I'm going to have a summation of, and again, you pull the I out, and I to the 1 is I cubed is -I to the 5th is back to I to the 7th is -I. It just goes positive, negative, positive, negative, positive, negative. That's another alternating series. So it's -1 to the n. And now we're doing the odd ones, so it's 2n plus 1 factorial, because those are odd numbers. X to the 2n plus 1. I forgot to do the power of the -1. Any of you recognize this? Very important. Any of you recognize these two terms? -1 to the n over 2n factorial, x to the 2n is sine of x. Plus I. And -1 to the n over 2n plus 1 factorial, x to the 2n plus 1 is cosine of x. So this relates exponentials and sines and cosines in a beautiful way. Okay, and I'm not going to do the full proof because we're about out of time, but I got to do this. I can't resist. And that is sine of x is equal to e to the x minus e to the ix minus e to the negative ix all over 2I. And cosine of x is very similar. Is e to the ix plus e to the negative ix all over 2. These are huge formulas. It means that sine and cosine can be written as exponentials. And then all the formulas are so easy to prove if you look at them in this way. And in particular, what if x is 1? What if x is pi? Then we're looking at e to the I pi. What do you get? What's sine of pi? Oh, you know, I have this backwards. This is important. It's this one. So what do you get if we plug in pi for this equation? Almost. Sine of pi is 0, cosine of pi is -1. So e to the I pi equals -1. This is one of the most famous equations in the world, in the universe, actually. E to the I pi is -1. You'd never guess it. I mean, why should you get -1 out of that? But you do. And it comes right from this big equation. And it went fast. So if I messed around with an I and missed it, I apologize, but I think I got it. Yeah. But we're out of time. And this is actually the last thing you'll ever see. So I wanted to end with this because this is like almost as famous as the Pythagorean theorem. E to the I pi equals -1. That's a biggie. So it's a good way to end the class. On Monday, we will review for the exam that's on Wednesday. And then on Friday, we'll review for the final. So there's no new math to do. Now it's just review and take tests. But as always, right now, I have office hours. So I'll stop the recording.